So I wanted to go over that derivation of reuse the Taylor expansion. So let's do a little more review. So recall the binomial expansion. Okay, so the binomial expansion is going to be something of this form. It's 1 plus x to the n. And this x here has to be less than 1. Okay? So what does that equal again? And we're going to be using this like 8,000 times next semester. It's going to become your bestest friend ever.
X to the n.
What's the first term? 1. First term is 1. Plus nx. Plus
n minus 1.
N times n minus 1 over 2 x squared plus
n
minus 1 n minus 2
over.
Hey! Perfect! Yes, you got it. 3! Because there's an exclamation point. So you have to raise your voice. Okay? It's true. It's true. X cubed plus. And it goes on and on. That makes sense? Now here's where we're going to use it a lot. Okay, what happens if you take a number less than 1 and square it? Get larger or smaller? So let's say you take 0.1 and square it. Bigger or smaller? What happens if you cube it? Even smaller. So if this number here is, let's say, really small, how does this term compare to this term?
Much larger.
And this term's going to be significantly larger than this. So what you're going to do is that if this is the case here, if you have, if this x is much less than 1, and we're often going to have that, what this expression here becomes, okay, is approximately 1 plus nx. That makes sense? And so this is actually where you're going to use this a lot. And we're going to see how we're going to use it today. So, and again, this is a special case of the Taylor expansion. What are the other Taylor expansions you're going to use a lot of? There's 3 in particular. This is, okay, 4. But there's 3 in particular you're going to use all the time in engineering and in physics. What? Okay, just function-wise, what 3 Taylor expansions of functions you just really have to know well? Blair, you can do your homework. I hate it. You can do your homework. Which one? Sine of x, cosine of x. Tangents actually that's you can, but that one doesn't occur as much. The exponential. Okay. Let me just say a little bit more about this. Okay, this is an aside. Okay. What is the cosine of x? What's the Taylor expansion? What's the Taylor expansion?
-1.
1. Minus x squared over 2, which is 2. Okay, plus okay, let's have a different conversation. What's the Taylor expansion? Okay.
Oh, so we were looking the same time.
Yes, it is. Okay, so here's some word function, f of x. Doesn't matter what it is. Okay. What we're going to do, we're going to take some point, we're going to call x naught. Right here. Okay. And what do I want to do about that point x naught? I would like some sort of series that approximates that function in some region here. Okay? So I'm going to have a region here. I'll go like this. Okay? What is that distance here called? The radius of convergence. Good. And I'm going to have a power, oh, but you can put your homework right there. I'm going to come up with a power series that basically approximates that function within that series and within that radius of convergence. Meaning, I have something that in this region here might look like this. So here's my little region here like this. I might have something that comes in like this. So kind of look more or less like this, and go like that. Who knows what it's going to look like? But in this region here, that purple line, which is the approximation, is going to more or less mimic what my function is. Okay? And this purple line here is a power series. Okay, so this right here, I'm going to say this f of, I'll just write it. I just really like this. What does it mean to be a power series?
X to some power.
Okay, so I'm going to have a0, a constant, okay, plus another constant a1 times x minus x naught. The point I'm doing the expansion about for the first power plus some other constant a2 x to the x naught squared plus no. That makes sense? And I want this right here to equal this function in that region here. So I'm going to equate this to here. That makes sense? So what do you have to find now? You have to find the constants a0, a1, a2. You have to find all those constants. So how do you find those constants? Let's start with a0. Okay, what happens if I put in x naught here? If I say x equals x naught, I get a naught here. What does this term become? 0. Because it's x naught minus x naught, so 0. This term becomes 0. All the terms become 0. So what I have here is that if I do this, just f of x naught equals a naught. Hey, I got the first term. Woohoo! Good. Now, how do you then find the second term? How do you find the a1 term? I couldn't hear what your voice is so soft with that stupid thing running, but I don't. Again, I think the off switch turns out to be right here. And so you take the derivative. Okay, so if I take the derivative, the constant gives me 0. This term gives me
A1,
okay, so this will give me a1 plus this term gives me
A2, X, it's not the first power.
yeah. So this the 2 is going to come in front. So I'm going to write this as 2a2 x minus x naught to the first power. To kind of show the pattern, I'm going to do one more. If I had the third term, what would this one give? The third term would be what? A cubed times x minus x naught cubed. So that one give me then? This will give me a 3a3
Square.
plus so and so. Hey, how can I now find a1?
X naught.
Yeah, I'm going to evaluate this at x naught. So I'm going to let x equal x naught. So I'm going to get this term here. Evaluated at x naught. This will give me a1. What happens to this term? 0, 0. All the other terms are 0. Hey, now I have 2. I only have, infinity minus 2 terms to go. Okay, we'll do one more, then we'll see the pattern. Okay. Hey, I'm going to find a2. Take another derivative. Okay, so take the derivative here. My a1 is 0. This term is 2A2, which was a Star Wars character. They helped, save the rebels. Okay, 2A2 did. Okay, turned out to be R2D2's not so bright cousin. So, it's true. Okay, plus this one.
683 minus 6.
And now this is 6, but I'm going to write it stupidly. Okay, I'm going to write it as 3 times 2 times A3 x minus x naught corresponding to so on and so forth. Hey, how can I now find A2?
X equals 0.
No,
Or
a
X
lot.
equals X.
Yeah, I'm going to let x equal x naught. So this gives me the second derivative here. This would equal 2A2, and then all the other terms give 0. So my A2 term is now 1 over 2. At that. Okay. How do you then find A3? You do another derivative. So if I do this one, that will give me this 3 times 2 times A3 plus like that. And again, I evaluate this at x naught. They go to 0. And so this gives me the A3 is this 1 over 3 times 2 here, x cubed at x naught. So if I want the a nth, first of all, 3 times 2 is the same thing as 3 times 2 times 1, and 3 times 2 times 1 is 3. He passes. See, you got it. He understands that. 3. That's what it is. That makes sense? So this goes to 3 factorial. So if I want the a nth term, in general, an is going to be what?
Over n.
Excellent. 1 over n.
D to the n f over dx n. X naught.
Very good. That's what you have. So I can say here is this is going to be this f of x is going to be the sum from, let's say, n equals 0 to infinity of a n x minus x naught to the n equals the sum here, 1 over n factorial This is your Taylor series or Taylor expansion. Now let's do one of the most common ones. What is the Taylor expansion sine of x about x naught equals 0? But out of curiosity, what is the 0th derivative of something? That's weird. What's the 0th derivative? You have to define it to be something.
1.
It means it's no derivative. So the 0th, if you have n equals 1, that's your first derivative. If n equals 0, we're going to interpret that to mean no derivative. So it's just going to be the actual function evaluated of x now. Okay, so you tell me how to do this. What is a0, right? So this, if I want this, I want sine of x. It's going to equal what? It's going to be this a0 times x minus x0 to the 0 power. This a1 x minus x1, 0 first power. It's a2 x minus x naught squared, so on and so forth. Okay. And this whole thing here, this is my an. So what does this tell me to do? This a1 termer is going to be what, according to this?
1 over 0.
And this is 1 over 0 factorial times the 0th derivative of this. I evaluated it at 0 because that's my x naught. By definition, what is 0 factorial? That's 1. This is just your original function evaluated at x naught. If I take sine of x and evaluate it at 0, what does that equal? That equals 0. So this is my a, this is my a0 term. So this term is out. Okay, what is a1? One over 1 factorial. First derivative here. Evaluated at x naught. So this is 1. What's the derivative of sine of x? Okay. Cosine of x, and this is going to be evaluated at 0. Cosine of 0 is 1. So this is a 1 here. This is a 0 here. So if I start putting these pieces together. Zero. Plus I'm going to get 1 times x. Plus, okay. Now let's do the a2 term. Let's go over here. What is this a2?
1 over 2 factorial.
Over 2 factorial, second derivative of that with respect to x. Evaluated at 0. Okay. So this is 1 over 2. What are two derivatives of the sine of x? Minus sine of x. Because evaluated at 0. What is that?
0.
So this is 0. The next term is going to be plus 0. Let's stop after the next term. Okay, so let's say the third term. The third term would be, a cubed x minus x naught cubed. Let me check to make certain that this is still on that board. It is. Good. So my a3 is 1 over 3 factorial. Third derivative of that. And evaluated at 0. So this is 1 over 3 factorial. What is the third derivative of sine of x? First derivative is cosine. Second derivative is minus sine minus cosine. Okay, minus cosine at 0. Cosine at 0 is 1. So this is minus a third factorial. Minus 1 over 3 factorial. This is minus 1 over 3 factorial times x minus 0 cubed, and then plus dot, dot, dot. So this is sine of x is what? X minus 1 over 3 factorial x cubed. To do the next term, look at the pattern. What's the next term going to be?
Over 5 factorial.
5 factorial. So the fifth, and then
1 over 7 factorial.
minus 1 over 7 factorial.
So the 7th.
X to the 7th, and then they alternate like that. Okay, if you remember, now, if x is really, really tiny, what does this reduce to? So if x is much less than 1, I can say sine of x is approximately just x. Where have you seen that? And I'll give you a hint. It's at the beginning of this course. Early on in this class, what did I have you do? Derive the derivative of sine of x. Remember that? Yes? Where have you seen this again? Well, let's get one more, then I'll show you exactly what we used it. Now, without doing any work, tell me how to get the cosine term now. I could go through the exact same procedure here and do it, or I can be lazy. How is a sine connected to a cosine?
Cosine is the root of sine.
Hey, so what can I do to this expression to get that?
Shift it over 1.
Put what you said correctly into words. Take the derivative of this with respect to x. So I can say that the sine, the derivative of, I can say my cosine of x is the derivative of my sine of x. Let's just do this. What is the derivative of x? 1. What happens if I take the derivative of x cubed?
Becomes 3 squared.
3x squared, but this is divided by 3 factorial. It's just 3 times 2 times 1.
So
And this becomes 1 over
it's
2, or 1 over 2 factorial. Hey, what's the derivative of this one? X to the 5th is
minus
5x to the 4th. 5 over 5 factorial is
1 over 4
1
factorial.
over 4 factorial. This. Okay? Those you just have to know for the rest of your life. They occur everywhere. Absolutely everywhere. Now let me just show you where they come in. Okay, I wasn't planning on doing this, but there's too much of a delay in your response. And so this, you just have to have cemented in your brain. So recall. Was it in homework 2? Maybe homework 1? Something like that. Okay. You approved that the derivative of sine of x dx was cosine of x. How did you do that derivation? Okay, you can just put your homework there. I mean, why do I call you Molly, brother? Okay. Because I'm stupid. I'm being stupid. So what's the formal definition of a derivative? Limit of delta x going to 0 of f x plus delta x minus this and delta x. So if I have this, what do we have? We have the sine of x plus delta x minus the sine of x all over delta x. What did we do, my buddy, here? We did this. That's the same thing as sine of a plus b. So what happens here? We have the d sine of x dx equals what? We have the sine of x cosine of delta x plus the sine of delta x cosine of x, right? Minus, so this whole thing here. This is my sine of x plus delta x. Minus my buddy here. All over delta x. Okay. What do we know about the cosine of delta x if that delta x is really small? Yeah, remember what we have here. We just showed that if we have the cosine of x, this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot dot dot. So if this x here is much less than 1, like our buddy delta x here, what happens to these other terms? Well, they don't cancel. They are small compared to this fellow here. So what I have here is that this is approximately 1. So this goes to approximately 1. Hey, what do we know about my buddy here? Sine of x as well. It's going to be this x minus x cubed over 3 factorial. It's x to the 5th over 5 factorial. If this is really small, what does this become? Pretty much x, because this is small compared to here, and that's even smaller compared to here. So this is x. So we made this right here x. So that gave us what? That gave us sine of x times 1 plus this. This was the delta x. I'm sorry, because this is my thing here. Delta x cosine of x minus sine of x or delta x. They cancel. And what happens here? Delta x cosine of x, delta x, they cancel, and that gives cosine of x. So you've used this before. I gave you a little geometric argument for why that was the case. but you've actually used those before, you didn't think about it. But they're used absolutely everywhere, those Taylor expansions. That makes sense? If you do anything with the numerical analysis or computational physics, you use them all the time. Because what you do is you're going to have a really rotten differential equation, which you're going to have no clue what to do with. It turns out you use a Taylor expansion to write those expressions into different expressions. And then you can put that on your computer and you can code it. So that Taylor expansion does not go away. It's used absolutely everywhere. It is one of the most important things you learn in Calc 2. That makes sense? Okay. That was a little bit of a digression, but I think it's an important digression. Hopefully that helps at some level. If you take more courses with me in physics, especially upper level courses, you're going to see that exact same discussion again. Because I want to make sure that that's completely pounded into, and I really mean pounded into all my students, because they just have to know this backwards and forwards because it's used absolutely everywhere. Okay, so now let's go back to what we were doing. Okay. So this was a PSA, public service announcement. Okay, now back to the class. Okay, so what were we doing in the class? Okay, so back to class. Okay, all right, back. So recall what we did yesterday. We had this expression here, 1 plus x to the n. And we said that this was here. Okay, and we said that if this x is much less than 1, this term is going to be a lot smaller than this term. So this term here is approximately equals 1 plus x. Okay, so now let's use that in what we're doing today. Yesterday. So last time. So in the last class, we proved that the real expression for potential energy due to gravity was this minus G big M little m over R. And the picture we had for this was, this is the radius of our planet or something spherical, doesn't matter what it is, as long as it's big and round. This is M. Here's a little m. The distance from the center to there is R. Now, the question is, how is this? Is this related to MGH? The reason why I'm hitting this is, first of all, it's important. Most books do not show you this. And they should. The other thing is, next semester, we're going to do this all the time. So we have to really have it understood. What was this H again? This H is the distance above the ground. So in this case here, this is H. All right, so if we looked here, if I draw a little stick figure, this is us, and the H here is the distance above the ground. So this little R here, the R going from the center of the planet, whatever we're at, on up to here is going to be this R, the radius of the planet, plus that little H. That makes sense? So I'm going to take that, and I'm going to put it in here. I'm going to say gravity, which we showed was this, becomes that. Now, what did we do last time? We took this big R, and what did we do? We pulled it out. And what did we say this has to be such that if we take this times this mess in here, we get back to R plus H. First term was a 1. Good, right? Because R times 1 is my buddy R. Plus, what does this have to be such that R times this mess gives me my body H,
H over R.
H over R. Right, so this times this is this, and this times this is this. Now this term here, I can raise it up to the numerator. And what do we know about H compared to R? Yeah, let's, we're gonna let H be much less than R. So this H here is not the distance of the moon. This H is gonna be 3 feet compared to the radius of the Earth. Okay, so this whole term here, this whole H over R is gonna be much less than 1. Hey, well, what is this? This is of the form 1 plus x to the n, right? 1 plus x, this is acting as my x, to the n power. So this is my x. And this is my n. What did we just state? That this is approximately 1 plus nx. So let's see what that gives me. Just so you know, the first time you see this is terrifying looking. You think, oh no, I'm dead. Probably not. Okay, but the first time you see this is really intimidating. That'll get more intimidating next semester. Just so you know, you're going to find out that first week in class. You're going to go, what happened to the class? It wasn't like this in the first semester. Yeah, that's just the nature of the beast. You probably know some people who are in the second semester of physics right now. Ask them how this second semester compares to first semester. They'll have a little conversation with you. Okay, so we get U gravity. Okay, it's then going to be this minus G. I'll put a little approximate symbol here. Big G, big M, R. And then I'm going to expand this person here. So this is going to be 1 plus my value N. Here's my N. And then here's my X, SR over H. I mean, this H over R. So this is 1 plus NX. I can multiply everything through here. You get minus G, big M over R. And then minus and minus make a plus. So this is plus G, big M, H over R squared.
Thank you, little one.
I need a little one here, thank you. Okay. That makes sense. Now this is just a constant. But what is this right here? We've seen that before. That is our friend. You calculated one of these on the homework.
Gravitational force.
Acceleration.
Okay. So this is nothing but little g. So what do? I have that this is equal to a constant plus m little g h. Okay, we always measure gravitational differences usually. So this constant has no effect on anything. But here's my buddy mgh, and that's the connection. That makes sense? It's a very subtle argument, very, very subtle. Let me give you a graphical idea of what's going on here. Graphically, we did the following. Okay, if I were to say graph this, if I were to say graph that, what would that look like mathematically? We basically have minus a constant over r. Right? minus constant over R. What does that look like? Well, if R is small, what is minus something over small?
Very good.
It's going to be big in the negative direction, right? So it's going to be negative. If I'm at small values here, so this is small, this is going to be giant. If there's a minus sign, this is going to be really, really down here quite a bit. As R gets big, what does this do? It gets smaller. So this is going to be something that looks like this. Okay. Now let's say here's the radius of the Earth right here. This is R. Okay. And let's say this is my distance h. This is R plus h. This value, this distance right here, that's my buddy h. If I look right here, mathematically, what does that look like in this little region here? Okay, if I had to say graph this, if I had to graph you gravity here, this is near the surface of the Earth versus h. MGH is nothing but a, in the words of Scooby-Doo, great Ryan Raggy. Great Ryan Raggy, constant. Straight line, Shaggy. It's a straight line, right? This is y equals mx plus b. This is your m, this is your x, and your b is 0. So this is going to be a straight line. Okay, if you look here, your u gravity looks like this. Here's my surface of the Earth here. This is the distance above it. That little function here, that little region here looks like a straight line. That's all we've done. Okay. That's a really, really subtle point. Most books will avoid it. Okay, I like subtle points are important. I was really frustrated because going through, no one explained the subtle points to me. It took me forever to figure them out. Does that make sense? Again, in physics, you have to know remarkably little. The catch is the tiny little amount of information you have to know. You have to know well. That's the catch. This is part of knowing something well. Questions? Okay, so let's say you're going to work with SpaceX, and we've sent a number of students to actually do internships at SpaceX. Every single one of them loved it. And so you're going to send something up into space. Okay, how fast does your rocket have to travel to leave the Earth? How fast must a rocket travel to leave the Earth? It doesn't even have to be a rocket, it could be anything. Anything. Travel. So you're hopping your parents' car, you step on the accelerator, speedometer goes up and up and up and up and up. At what point do you have to worry about that needle hitting some spot, but your car is just going to take off? I'm sorry, Mom and Dad, I didn't mean to take the car. I didn't think the Honda Civic could go that fast. I'm sorry. Those things happen. Okay. So let's draw a little picture. Earth. Here's radius of the Earth. Here's my little rock. I'm going to set it up with some velocity. I'm going to call this V escape. This is called the escape velocity. This is m. So first of all, we have to figure out escape. Okay, where is escape? This escapes. It gets up to here, and what are we going to call the R for this? Infinity. This is R equals infinity. And if you just reach infinity, which you can't, this is a theoretical construct. What is going to be your velocity if you just get there? 0. So if you just get to, because you could go faster than that, in which case when you get to velocity, you're going to be moving. When you get to infinity, you're going to be moving faster. But if you just get there, your velocity here, so v at infinity, at r goes to infinity equals 0. What does that smell like? You start here, you finish here. This smells like conservation of energy. Okay, so this is an E initial equals E final. Okay, energy is made up of what two pieces? Kinetic and potential. Okay, what is your kinetic energy on the surface of the Earth if you're just escaping? What is kinetic energy always?
Half mv squared.
1/2 mv squared. So this would be 1/2 m v escape squared. Now, can I say my gravitational potential energy is mgh?
Not closely.
Yeah, you could, it's for the entirety, exactly. So you could say, well, here you're close to the surface of the Earth, sure. But it turns out infinity is not close to the surface of the Earth. So you can't use that. Instead, what do we have to use? Minus big G, mass of the Earth, little m over the little r. And where does the little r go from? The center to the sphere. What is this distance here called? Radius of the Earth. So this would be minus G, the mass of whatever planet we're on, m, over the radius of your planet, okay, equals. If you just get to infinity, your velocity, your kinetic energy is 0. And what is this gravitational potential energy at infinity? We define that to be what do we define it to be? Okay, so what's your little r in this case?
Oh, so 0.
Infinity, so it's 0. Remember, we defined the potential energy to be 0 at infinity. So this is plus 0. So this is 1/2 m v escape squared equals this. They cancel. Take over the 2, take the square root. So my escape velocity is 2gm over r. Does that make sense? Now, that has really neat implications here. If you land on a planet, what would be really nice for that planet to have? Oxygen, or just actually just in principle, an atmosphere. Okay, so to have an atmosphere, right? Your gas molecules in the atmosphere are moving. What did that velocity of the those gas molecules better not be?
Greater than.
Yeah, better not be greater than the escape velocity, because what's going to happen to your atmosphere? It's going to leave. Okay. Well, that idea, where does helium come from? Comes from balloons. Yeah, it goes in balloons, fine. Well, where does helium come from? Okay, it does come from the Earth. It does come from the surface of the Earth in the interior. But from what? It's a byproduct of radioactive decay. In particular, what particle? It can come from uranium, okay? So what happens with the larger nuclei? They actually give off an alpha particle. What is an alpha particle? So you might have uranium 238. This is 92. What can happen? This can actually give off an alpha particle. And what is an alpha particle? It's a helium nucleus. It's He4, 2, so this would go to 234. This is thorium, and then this is nitrogen. So this is the alpha particle. What happens when it moves slow enough, it acquires 2 electrons, it becomes helium gas. Okay, so helium actually comes from the surface, it comes from radioactive decay. It's actually, and if you're being honest, it is really the only non-renewable resource that exists on the Earth. It's the only one, because what, and this is why. Okay, so it gets out here, and you can actually, so those molecules are going to be moving around. If you're to make a plot of the number of atoms with a given velocity, you plot the velocity here, you get this curve that looks like this. It's called a Maxwell-Boltzmann distribution. If you actually put in the mass of helium, it turns out that here's your escape. What's going to happen to all these helium molecules there? They're going to leave the surface of the Earth. And then what happens? Well, then interactions occur, and then basically this tail gets refilled, and they would leave, they would leave. In principle, why don't we all sound like Donald Duck? You know, if you breathe in helium, you sound like Donald Duck. Why? It's because basically that helium actually leaves the atmosphere. Because that velocity, the velocity of these particles exceeds actually the escape. Okay, that's why helium doesn't build up in our atmosphere. Now, if you had a planet that's actually small enough, what could happen? If you had a planet that didn't have enough mass here, if it was small enough, didn't have enough mass, that V escape would be small, and you could actually lose your atmosphere. That's kind of neat. And just out of curiosity, let me just complete the discussion. Okay, where does our atmosphere come from? This is kind of fun. Volcanoes. Okay, so here's the Earth. We have volcanoes like this. Here's a little volcano. Here's a little volcano. Here's a little volcano. Work with me. Okay, they erupt, and what happens here? You basically get all the volcanic gases going like that, and that's where we get the atmosphere from. Okay, so our atmosphere initially came from volcanoes. Now, what about Mars? Does Mars have an atmosphere? It does, but it's very weak. Now, so here's Mars. Most of Mars is here. And it has Olympus Mons is actually, I think, the largest volcano in the entire solar system. It's no longer active. So here's a volcano on Mars, this is Mars. Volcano, and this would also have an atmosphere. Now it's smaller, so the escape velocity is lower. So it will lose part of its atmosphere here. But what happened early on in when our sun was basically starting to turn on? When the sun was just starting to actually, when it was young and still forming, because it was called a T-Tauri stage, and it basically has these really violent solar winds. So these solar winds come, and they actually, hit the Earth here, they hit the Mars here like this. And what can happen is actually they can strip off the entire atmosphere here. Now, Mars is small enough that what happened here is that Mars is small enough that the entire interior cools. If the entire interior cools, what happens? Plate tectonics stops. You no longer have volcanoes. Okay, and also it means you no longer, since you don't have a liquid core anymore, it also means no magnetic field. So Mars doesn't have a magnetic field. The sun was still turning on, had these violent solar winds. This atmosphere of Mars was completely, for the most part, removed. And since the volcanic activity was very weak, Mars is now left with a very weak atmosphere. But our planet is a little bit bigger. So what do we have, fortunately for us? We have a liquid core, which means that we have plates that move, which means we have volcanic activity. And it also means we have a magnetic field. So what happens here is that you have the magnetic field from the Earth like this. So when these solar winds hit, what happens is that because of the magnetic fields, the magnetic fields took these solar winds and actually would direct them like here and actually would protect our atmosphere. So part of the reason why we have an atmosphere is we're bigger. So we have an active core, we have a liquid core, we have a magnetic field. That magnetic field actually then prevented basically these solar winds from stripping our atmosphere. Okay, pretty cool. Okay. If you want to know more about stuff like this, is that we have a new colleague in physics. His name is Connor Robinson, and what he does is he looks at planetary formation. He worries about things like this. Okay, he's very good. In fact, he actually has time on the James Webb Space Telescope, which is ridiculously hard to get. That's how good he is. Okay. It all goes back to this little humble equation as well. Okay, so what we're gonna start tomorrow is a brand new topic. We're gonna let things smash together. We enter collisions and we get linear momentum. Have a great day.